The last tab is the drainage file. The drainage here actually specifications of how far away the drainage system from your irrigation system, and also how deep your pipes or drainage pipes below the surface, and also how big is the diameter of each pipe. The other thing also the depth of the groundwater or the water table, as well as the salinity, ammonium and nitrate and urea concentration of the groundwater. There is one parameter here, is that hydraulic conductivity in the horizontal direction. Most of people find it difficult to measure the horizontal hydraulic conductivity, and we actually have here option that you can calculate it as a fraction of the vertical conductivity, which is easy to measure. So we measure the vertical conductivity, and as a rule of thumb, we sometimes assume the horizontal is 1/3 of the vertical conductivity, and we use it here. So that's really maybe the last tab in that. Once you fill in all those tabs, and then you go there and you save this information you put in there in a text file. So you go to save as, and we can call that as a trial or Aachen trial SMC file, and we can save it there in the example files. So that helps you next time you don't put all this information again. So next time you run a model, you go to the model here and say, I would like to have my last file, or I open a new file. If you go for last file, and it should actually bring back the file that we have been busy with, and this is really, we should be able to see the name of the file here, Aachen trial SMC file, and you should be able to see the information, for example, that you put here everywhere on those little boxes. So that's really how the model works, but of course you have more information in the guide. So now I will bring another SMC file to you to see how the model runs, and I will open one of those files which can give you more comprehensive coverage. So these are 8 fields, and the SMC file, which has got all the information and links to input files, will be uploaded, and then everything here that's field number 8. And if you go to all the fields here, basin, line, trickled source, rain-fed, sprinkler, PRD or partial root drying, subsurface variable frequency, and also you have subsurface trickle line source. You have here PRD but fixed frequency, and the drainage system. And for each of these, if you click on any of these here, for example, that's especially the PRD, and if you look at the irrigation here, that's quite different from other irrigation, because here you have 2 drip lines, and the drip line to the left, that's the discharge, and the drip line to the right is the discharge. It should be here. And there are some times that you have here the drip lines on the left side is working, while on the other side, the right side is not working. And that's the meaning of PRD. So you have one line of dripper working one day, and the other one not working on that day. But after that, they swap. You can see here, the left dripper here started to work, and the right is working and the left is not. While the days before, you have the left was working and the right is not working. So that's your alternate, and that's why in that particular case, you have to specify it is a file defined frequency and PRD. So here you have PRD mode, file defined frequency. So the model will read from the file whatever the days are, because sometimes you get rainfall, and the rainfall can disturb the frequency. So sometimes if I have rainfall, we don't irrigate and we wait. So there's no fixed number of days in such case. So here we have that example, but let me go first to the presentation here to give you an idea of what you are going to see. This is example of evolution of soil moisture under trickle line source, where here the soil moisture comes here under the dripper, and you can see the ranges as the motor goes on and on. This is salinity distribution. This is what you expect from the model. And if you have subsurface drip irrigation, this is really the plot you can see. The model here, or the drip here, is below the surface. And this is a case of basal irrigation, where you have only vertical flow. You don't have horizontal and vertical flow, but everything just goes by gravity. And this is what you see as a soil moisture profile and soil salinity under one-dimensional flow or basal irrigation. Sometimes you get soil with heterogeneity, and the different layers, they behave different, and you can see the different layers, they have not homogeneous soil moisture distribution. And also you can see the soil moisture profile reflecting the different three layers. In the PRD system, usual drip irrigation, we irrigate the whole root zone, so the right and the left side of the roots, they get the same water at the same time. When we apply partial root drying, we irrigate one side and we leave the other side dry. So we irrigate half of the root zone and we leave the other half dry, and then we alternate. So the next time, that side that was dry will become wet, and the one that was irrigated will not be irrigated and it stays dry. And this is really how we do it in the field. So you have on and off, you have two lines here, and we switch. So each half of the root zone will get irrigated once. And in the field, you can also do PRD with drip with furrow irrigation. So you can put once water here and leave that one dry, put water here and leave the other one dry, and next time you put water here and leave that one dry, and so on. So you can also apply PRD in furrow irrigation. That has been tried in Serbia as well. And PRD can look like this in the model, where you have here that dripper here is working, while that dripper actually is not. You can see the difference in color here. And also you can see the soil moisture profile, that you have here a higher moisture content because the dripper to the left is working and the dripper on the right is not working. That's why you see higher moisture content of the left dripper, because it is working today while that one is not in the PRD system. And here you can see the middle one is not working, but the right side and the left side, they are working and under the PRD system. You can also have a look at the nitrogen profiles, the same as salinity and the soil moisture, and that's the vertical distribution, and you can also see that as horizontal distribution from the drip line. Also the model interpolates the values between the three main input values of the crop coefficient. So for we get the crop coefficient Kc here, and we get only one value here, one value there, one value there, one value there, and the model actually calculates a daily value and then connects the crop coefficient and other crop parameters by interpolation. Evaporation is usually calculated in the model, and you can see here we calculate the total evaporation, and that's the combines the transpiration and the bare soil evaporation. So bare soil evaporation plus transpiration gives you the total evaporation. In the beginning, when the plant is too small, then most of the evaporation actually goes to bare soil evaporation, and as the plant grows and gets a bigger canopy, then the transpiration becomes the major contributor to water losses, and bare soil evaporation goes to the bottom there until harvest day. On harvest day, the bare soil evaporation starts to go up and transpiration goes down as you cut the crop. Also, the model can show you the irrigation and rainfall input to the model during the model run. So you can see exactly how much water actually is used by the model during the run. And also you have here, the model calculates the relative yield, and the relative yield can reflect the difference between the potential uptake and actual uptake. The wider the gap between the two, it means the plant was subject to stress, or water stress and salinity stress. So the red line and the blue line should be on top of each other if you have no stress during the growing season. The model also gives you the total dry matter and gives you the final yield here. And also the model can show you the nitrogen uptake and the total nitrogen uptake by the crop. And also can show you the nitrogen leaching to the drains and the cumulative value as well. One important thing of the model is it gives you the water balance and nitrogen balance and the salt balance. And usually you should see zero balance indication of the mass balance has been observed. And in case of the drainage system, the model can show you that plot. These are the drains, and here you have the drainage on top, and this is the shallow or the groundwater area. And here the model can show you the development of the water table over time, and it gives you also the average and the minimum and the maximum groundwater level over the model run. In case if you run the model for several years or crop rotation, the model also will show you that the period where you have change in evaporation and transpiration according to the time. And also you will be able to see during the crop rotation the crop yield and total dry matter for each time. These are the periods where you don't have anything growing between. The model actually we use in the model performance to judge the performance of the model. We use the root mean square error as indicator of goodness of fit. We use also the R square or coefficient of determination, and also we use coefficient of residual mass as defined by this equation. So these three parameters, we use them as indicator of goodness of fit. And if you need to know more about the model and the applications, you need to go to these publications. But when you download the installer, there is a folder there, and it is named publications. And look for all those publications; they are in that folder.